Hello, good morning, everyone. Thank you for joining us. Uh, Thank you for attending this webinar. Just giving it a minute or so, so all the attendees can be with us. Okay, let me slowly start. So, welcome everyone. Good morning. Thank you for joining us for this BATT4EU Success Stories series of webinars on the solid-state batteries. Before we start, just as my colleague Virginia is writing in the chat, a little bit of information for you. The slides will be shared. Please make sure that you write your questions in the Q&A section. Unfortunately, we don't allow mics for the or speaking for asking for questions because of the shortness of time. But you're free to indicate your questions in the Q&A. So let's start. This is a very kind of a packed agenda, a lot of information on a very important technology. So, but before we start, just a little bit about ourselves. So let me introduce myself. I'm Bozor Khanbhai. I'm the Executive Director of Batteries European Partnership Association. And BEPA is the private side that in cooperation with the partnership enables the BATT4EU partnership. The BATT4EU partnership is the co-program partnership under Horizon Europe. Developing the funding for the battery industry, battery sector, and battery RNI community under Horizon Europe. So, has a goal of mobilizing around 900 million euros for the duration of the Horizon Europe for battery projects. And of course, I hope you have more about BEPA, but through that partnership and through the experience that we got and through the goals of the partnership, we have conducted many activities to enhance the connectivity of the ecosystem and make sure that it aligns with the EU goals in general, and try to make the value chain as competitive as possible. So please, we have a lot of events and webinars. Please have a look at our website and make sure you are updated with BEPA activities and our ongoing activities for the duration of the year. So there's a lot to talk about solid-state batteries. From our side, I just give you a quick snapshot of how we have funded these projects under BATT4EU partnership. It has been on the top of the agenda for us for the duration of the Horizon Europe. This is a very important topic. The future of the automotive sector specifically, but other sectors like aviation and other high demanding sectors in terms of batteries depends on this technology, depends on the scaling of this technology, and depends on the development of the components of this technology. So it has been always in the agenda for us to support, and it's becoming even more important moving forward as we are seeing the results of these projects getting to the higher TRL, and that indicates and that demands even more support to make sure that the valley of death is filled and we can successfully scale up this important technology. So the work program for 2026 and 2027 is already out for you to review, but just keep in mind that we are having a very large projects for the solid-state batteries. I just give you one of them, the 105 million euros, almost 105 million euros. So please keep in mind that these are not final figures. We'll be supporting the manufacturing and the development, but we call the kind of integrated development of solid-state batteries. Almost 1/3 of it will go to the aviation projects So very important topic, very important. We are also keep supporting these projects. So we are gonna hear from three of these that started early in the Horizon Europe. We start with the we will have projects Helena, Advagen, and Psionic. One of them on the mostly on the aviation and the others on the automotive part. I give the floor to Pedro Lopez, who is the coordinator of the Helena project. So without further ado, please, Pedro, give us more information about the progress and results of the of Helena.
Yes, thank you, Bosro. Should I? Okay, so all right.
I,
I can
I,
see I can see the slides
yes,
now on the screen. Thanks, Bosro.
yeah, please let
Um,
me know to go to the next one. So
sure, I'll do. Um, all right, so hello everyone. I'm very happy to represent today our fantastic Elena consortium. As Bosorg was introducing, we are targeting this Gen 4 solid state batteries. In our project, we are focusing on two different applications for electromobility, for electric vehicles and aircrafts. So please, Bosorg, if you could go to the next slide. And so it's been already a long journey since we started in 2021. So my goal is here to bring first a very brief overview of the project and then some highlights of the main results that we obtained. Of course, there's a lot of things that I could not cover in this short presentation, but I invite you to follow us on the social media and to keep an eye on our scientific and technological advances. So this is the main concept of our cell, our battery device that we are targeting. So we focus on a halide solid state battery. So halide is, let's say, the core material is the solid electrolyte separator, as you can see from this schematic, in which we have a composite high voltage cathode with the halide solid electrolyte thin separator, a lithium metal anode. That is enabled by this solid state battery technology and a protective layer. So we have very specific objectives for the battery specifications for the automotive and aircraft end users, which are defined by our end user partners. And we also have specifications for the solid electrolyte, which needs to be a high ionic conductor to be stable with all materials within the battery. There is also development of active material as enable of the high voltage battery, and of course a lithium metal anode, which targets also very thin lithium metal layers with also protective coatings to improve the stability between the lithium metal and the high solid electrolyte. And of course, we are developing pouch cell prototypes, which aims to demonstrate a higher TRL of this technology. So we count on a multidisciplinary consortium from advanced materials suppliers, battery component developments, cell assembly players, partners doing the testing, aging, and the safety of the cells. On the battery modeling, we also have partners doing this transversal activity, and also partners working on the recycling LCA and LCO concepts. And of course, our end users, aircraft and EV OEMs that set the specifications of the cells. If you could go to the next slide, please. Yes, so where we stand now from since 2021, so we started by the development and of the core materials of the technology, which is the halide solid electrolyte, the cathode active material, and the lithium metal. And since then, we've been following the upgraded path towards the fabrication of prototypes. So we have optimized those materials to improve the electrochemical properties of the electrolyte, cathode, and lithium metal, and we also have developed processing routes to transform these materials into battery components. So that means solid electrolyte layers, composite cathode electrolytes, composite cathode laminates. And now we are on the step of assembling prototypes uh, on the scale up from lab coin cells to monolayer and multi-layer pouch cells. If you could go to the next slide, please. Yes. So in terms of materials that have been developed within the project, so this is an innovative project which relies on new halide solid electrolyte material. So this electrolyte is the core of the technology in this regard. There's been several generation of solid electrolytes that have been developed based on lithium, yttrium bromide, and chloride, and some dopants. And we've been targeting several requirements for the solid electrolyte, ionic conductivity as one of the main targets. That we've been able to optimize it up to 5 millisiemens per centimeter. We've also worked on decreasing the particle size of this solid electrolyte, as that is key to ensure high performance of the cells and good contact with the active material particles. And so in this different generation of halide electrolytes, we've been able to finally target an optimized composition that is going to be used in the final devices. On the same side, on this, the active material also has been developed within the project, targeting two different nickel-rich high-voltage cathode. NMC. We started with the NMC 622 with a capacity of 170 milliampere hour per gram, and now we are progressing towards the NMC 811, which delivers a higher energy density. So again, also in this case, we have adjust the morphology of the active material as long as the particle size and the coating, with the focus as well on the recyclability of this NMC material having high added value of transition metals in their structure. If you could move to the next slide. Yes, so this is where it becomes more interesting within the project, where we already from the optimized materials, we've been working on the processing of these materials to transform them into battery components, which are the value materials for the prototypes. So on the halide side, we've been processing these materials with specific binders in order to obtain self-standing separators. Here we are targeting very thin self-standing membranes in order to reach high energy density cells. And so, as you can see, we've been able to move from very thick densified pellets to self-standing membranes of around 60 micron, already having quite good ionic conductivity. Of course, it decreases with respect to the halide pure material because it has some non-conductive materials such as the binder. But it's still having conductivity beyond 1 millisiemens per centimeter, which is required for high power applications. So that's on the side of the halide electrolyte. As well, on the composite cathode, we've been working on the formulation of the composite laminates, which include the high nickel content NMC with the halide electrolyte and the carbon. And as you can see here, we have developed composite cathodes with a high loading up to 4 milliampere hour per square centimeter to ensure, again, high energy density application. And here we're also looking for improved particle contact between the materials contained within the cathode laminate. And now we are on the step of integrating both the separator, the composite cathode, and the lithium metal into these 40 milliampere hour monolayer pouch cells to then scale up to multi-layer pouch cells of 1 to 5 ampere hour. Please, next slide. All right, so here's some results on the cell performance just at lab scale. So that means we take the materials, we assemble them in a small coin cell configuration, and we do the electrochemical testing in order to assess the performance of the materials. So here you can see some different setups with the halide solid electrolyte as separator, a lithium metal anode, and the composite cathode. And so what we have observed is that with the NMC 622, the material is able to deliver high specific capacity with a Coulombic efficiency that increases up to 98% after the first cycle. And we have also observed that there is a decrease on the specific capacity. This is due to the interaction and the interface between the halide and the lithium metal, which hinders the performance of the cells. And we have observed that having an interlayer, as protective layer of a sulfide aegirite, may improve also the cyclability of the cell. So we have within the project, we have a specific task on developing these protective layers to improve the compatibility between the lithium metal anode and the solid electrolyte. We've also shown that we can increase even further the capacity from this 100, almost 150 milliampere hour per gram, up to 210 milliampere hours per gram when we replace the NMC 62 by NMC 811 with a higher theoretical capacity. So please, next slide. All right. There is also a transversal activity within the project, which is the multi-scale multi-physics modeling framework. This, as you can see here, this hierarchical approach, a computational approach. The goal is to help to the experimental activity to improve the materials properties and to enhance the battery performance with this modeling framework that starts by at low-level atomistic modeling and goes up to system simulations into module and packs, encompassing also the microstructuring modeling of electrodes. So here the goal is not only to improve materials and battery performance, but it's also to be able to predict the battery performance in the long term cycling. And here is some example that you will see in the next slide, in which thanks to ab initio molecular dynamic simulations, we were able to elucidate some important aspect of this technology, which is the reactivity between the lithium metal and the solid electrolyte interface, which is key to ensure high performance devices. So we observe from experimental symmetric cell cycling that the halide electrolyte was showing a reactivity with the lithium metal that was evidenced by an increase of the overpotential during the cycling, as you can see here on the pink And the pink curve, there were potential increases during the first hours of the cycling, and then it was decreased and being stable and lasting up to above 1,000 hours. We have observed with the experimental characterization tools that there is a formation at this interface of different lithium salt species, such as lithium bromide and lithium chloride, as well as yttrium metal. And so thanks to these computational tools, we were able to understand that this is an intricate and dynamic layer in which these elements are combined in different layers with conductive layers having lithium bromide and lithium chloride, and isolating layers, sorry, of lithium bromide and lithium chloride, and conductive electronic conductive layer of yttrium. So thanks to this computational approach, we were able to understand why it happens, this stabilization of this interface. If you move to the next slide, please. So it is also an important aspect of the
I'm so sorry for interrupting, but just to remind you that we have a couple of minutes left. So
yes, sure. At the finish.
sorry, please go ahead.
So sustainability on the project is also an important aspect. Here we are targeting recycling of the elements. It is here particularly challenging because we are dealing with novel chemistries, and here we are targeting recycling above 70% of the elements, and in this particular technology we are able to recycle even up to 80% of some elements like lithium on the solid electrolyte and on the cathode material. If you move to the next slide, please. Yes, so we've developed different strategy recycling routes, and based on thermal conditioning, mechanical treatment, pyrometallurgy, and hydrometallurgy. And we have already identified two paths which combine some of these recycling routes that are now being evaluated experimentally. So this will for sure be a very important outcome of the project in terms of understanding how these new chemistries can be recycled and contribute or impact on the LCA analysis. If you could go to the next slide, just to finish with some challenges of the solid-state battery technology. So we have understood that it's relatively easy to make lab-scale devices showing high performance, but here the main issue that we are dealing with is the solid-solid interfaces that need to be tackled in order to improve the long-term stability. And considering the industrial bottlenecks, if you go to the next slide, and I'm just finishing. So here, of course, one of the bigger gaps that we are facing is the how to upscale from coin cell lab devices to industrial prototypes of 1 to 10 ampere hours pouch cells. If you go to the next slide. Yes, so here there is the challenge of bridging this gap between the laboratory advancements and the pre-industrial prototypes, which mainly comes from the pressure that is required for this technology in order to compact, to densify the materials. And if you go to the next slide. Yes, so with this, I'm finishing with this very brief outline of the Helena project, and I invite you to follow us on the media, and of course to get in contact with us if you have further scientific, technical questions or any others.
Many thanks, Pedro. That was really interesting. It shows the comprehensiveness of your project. That's a difficult word, but it's interesting to see that you also tackled the question of multi-scale. It's also important to have that bigger image in mind, and you're working on a very difficult topic. So how the electrolytes are notorious, especially for upscaling and the vulnerability to humidity. So we're very very glad that there are projects like you that taking the question to the toward the answer faster. So thank you very much. Please, as you
Thanks to
mentioned,
you.
please get in contact with Pedro and hold this project if you have any questions. There are not a lot of big projects that work on this specific material and going to this journey. So it's a very precious information that we have, and you're very much invited to get in touch with the team. So thank you very much, Pedro. I move to the next presentation from Psionic project and Francesco Gambino who is the coordinator. So thank you very much for joining us. I give the floor to you. So please, Francesco, let us know about the progress and the findings of the psionics.
Perfect. Thank you for the introduction. I am Francesco Gambino, a PhD student from Politecnico di Torino. In the next slide, I will talk about this project, the Psionic project. Thanks. Exactly. This project in which I'm involved involves the collaboration between several research centers across the Europe and under the supervision of Margot Lecuyer of Blue Solution. Next slide, please. Exactly. Yeah, the main objective of Psionic is to design an advanced all-solid-state battery with a solvent-free extrusion process. The polyelectrolyte produced in this way will be employed with a lithium-engineered anode and a high-voltage NMC cathode to achieve unprecedented level of safety and ionic conductivity. Can you move to the next? Thanks. The Psionic project started with the kickoff of July 2022 and is a 4-year EU-funded project under the EU Horizon Europe Research and Innovative Program. The research and innovation carried out under the Psionic project will not only contribute to the technological advancement of all solid-state batteries, but will also enable higher uptake by the electromobility sector, paving a way to climate neutrality. So, go to the next slide. Next slide, please. Thanks. So this is where our work started. We started from the preparation of our polyelectrolyte. We employed an extruser to blend polyethylene oxide with polycarbonate at 140 degrees. The salt used was lithium TFSI in the constant ratio of 20:1. In this case, we selected 3 experimental variables: polycarbonate type, polyethylene oxide molecular weight, and blend composition, that are relevant to the production of the blend. Each of these factors can significantly impact the final property of the solid polymer electrolyte membrane. About the type of PO, we explored the effect induced by the variation of molecular weight using 2 distinct POs with molecular weight of 400,000 and 4 milligrams per mole. At the same time, we examined the influence of employing 2 different types of polycarbonate, namely polyethylene carbonate and polypropylene carbonate. The blend composition ratio and its effect on the final properties were also investigated, varying the percentage of PO from 0 to 100%. Next slide, please. This is noteworthy that the entire process is completely solvent-free, and by employing an extruser is easily scalable at industrial level. Next, please. After the production of all of the membranes, we started with the physical characterization, and we examined the morphologies of the polymeric blend composed of PO and PEC by SEM analysis. The micrographs on the left show the cross-section and surface analysis of the blend at 30, 50, and 70% of PO and PEC. All of them displayed a uniform and continuous appearance without evidencing any separate domain. This suggests that the PO and PC components are well homogenized and that our extrusion process is working well to produce this blend polymer electrolyte. However, from DC measurement on the right image, there were revealed two distinct TG of the polymers, indicating that there is no miscibility and that the microphase separation is present at the submicronic scale. Next slide, please. Also, from DSC, we were able to determine the crystallinity of all of our membranes. We can see that there is a constant decrease of crystallinity of the polyethylene oxide-based polyelectrolyte. When LiTFSI is added, there is a reduction of crystallinity from 70 to 35%. But when we added our polycarbonate, there is a constant decrease of the peak of the crystallinity, indicating that the membrane is becoming more and more amorphous. In fact, at around 50% addition of polycarbonate, we had a residual crystallinity around 8%, and any further addition resulted in a completely amorphous membrane with blend membrane with polyethylene carbonate displaying a slightly lower crystallinity than membrane with polypropylene carbonate. Next slide, please. After physical characterization, we also evaluated the electrochemical properties of our membranes, starting with the ionic conductivity. Despite both polycarbonates have very low ionic conductivity, around 10 to -9 for PEC and 10 to -10 for PPC, when they are added to the PO membrane, they cause an improvement in the ionic conductivity. This is caused by the decrease of the crystallinity induced by the addition of this polycarbonate. We compared the conductivity at 40 degrees of all membranes, reaching a maximum at 4.6 per 10⁻⁵ Siemens per centimeter for the formulation of PO 400,000 mixed with 50% of PEC. And after 50% addition of polycarbonate, there is a detrimental effect of induced by this polycarbonate. In fact, there is a drop in the ionic conductivity. Together with the ionic conductivity, we also evaluated the electrochemical stability window. Since polyethylene oxide is known to be a not very stable compound that degrades around 3.9 volts, while polycarbonates are known material to be more stable. In fact, we observed an effect by the addition of these polycarbonates, and using a threshold of 3 microampere per square centimeter, we compared the current developed by increasing the voltage of this material. We can see that the PO starts to degrade in fact at around 4.3 volts, while when there is an addition of the polycarbonates, there is a beneficial effect, and the electrochemical stability window shifts to higher voltage as the amount of polycarbonate is increased. Next slide, please. At this point, we selected one membrane to further characterize, and in this case, we selected the one made of PO 400,000 mixed with PEC in the ratio 1:1, because it displayed the best ionic conductivity among the series, and also the electrochemical stability was improved compared to the starting material. Next slide. We started the characterization of this membrane with lithium plating and stripping. However, at 40 degrees are present several spikes already at 0.05 milliampere per square centimeter, and when the current density was increased, the cell completely short circuit. Next, please. So we opened the cell and we observed a gel-like compound around the disc. This to investigate this, we also assembled an identical cell and we recorded the impedance over a period of 1 month. And we can see from the graph on the bottom right, we can the internal resistance of the cell is continuously decreasing. This can be explained by the low stability of polycarbonates in contact with lithium. They are known to be degrading and depolymerizing, producing the starting monomer. Next slide, please. So we tried to vary our process, so we developed at the beginning, and we introduced a photoinitiator that is stable at the temperature of the extrusion. Next, please. So again, we produced the blended polymer, but with the inclusion of this photoinitiator. And next, please. We hot pressed the obtained blended polymer, and after UV curing with an UV lamp, we were able to produce a cross-linked polymer. Next slide, please. This cross-linked polymer electrolyte membrane was self-standing, elastic, and with an improved thickness up to 60 micron compared to the previous membrane. Next slide, please. So the change in the composition of the polymer electrolyte was reflected in lithium plating stripping. At 40 degrees, it was not anymore short-circuiting, and the plating stripping was stable up to 0.2 milliampere per square centimeter. Also, at 70 degrees, the performances were improved, and it was showing a low over potential of 0.3 volt when a current density of 0.2 milliampere per square centimeter was employed. Also, we performed a prolonged plating and stripping experiment to ensure the stability and the safety of this membrane. And we can see that after 600 hours of cycling, there are any spikes or unexpected shift in the current that can account for an even lithium deposition or dendrite formation. Next slide, please. Also, we open the cell after plating and stripping, and we tested with NMR. So the opaque membrane, as I showed you before, was showing a gel-like compound after cycling. And in fact, the NMR revealed that before cycling, there are the peaks that can be attributed to PEC and PEO. But after cycling, there is a new peak that is demonstrated to be ethylene carbonate that is appearing, so confirming that the polyethylene carbonate is depolymerizing, forming the ethylene carbonate monomer and causing a loss of solidity of our membrane. In case of POPEC UV, instead, the membrane after cycling was still solid, and from NMR, we revealed that after cycling there is still the appearance of the ethylene carbonate peak, but in this case, the cross-linked network can retain this monomer produced, but can act as a plasticizer, also improving the ionic conductivity. Next slide, please. So we, after tested this polymer electrolyte in an LFP-based cell, we used a composite cathode with high loading around 10 milligram per square centimeters. Next slide, please. Okay, from the recapability test, we observed that at C over 20, there is the reaching of an high specific capacity at around 168 milliamperes hour per gram, and also with a very high Coulombic efficiency of around 99.8%. Also at C over 10, there is a great retention of the capacity that is around 100 and 60 milliampere hours per grams. But when we tested this membrane at 40 degrees, we didn't achieve the results that we expected to have. So, next slide. We are currently testing a variation in our membrane by the addition of a plasticizer. We expect that this plasticizer can boost the ionic conductivity at lower temperature, enabling the operation of a solid state cell at room temperature. Next slide, please. This plasticizer that we are currently testing is succinylnitrile. We observed an increase in the ionic conductivity compared to the membrane without succinylnitrile, and also the electrochemical stability window is really good due to the stability of the Charno group present in this molecule. Also, we performed some preliminary tests with an NMC-based cathode at 40 degrees. And as we can see, there is the reaching of good specific capacity at C over 15. We have a specific capacity of 130 milliampere hours per gram. So we are currently testing this membrane and further characterizing in order to achieve operation at lower temperature with NMC-based cathode. Next slide, please. So in conclusion, we were able to produce a blended polymer electrolyte employing an extrusion process. This process avoid the use of solvent and easily scalable to industrial level. Also, we didn't employ any flammable organic solvents, achieving all solid state batteries. The effect of the addition of these polycarbonates was to the decrease of crystallinity, boosting the ionic conductivity, and also the carbonate group induced an improvement in the electrochemical stability window. Next slide, please. Would like to thanks all the partner for the support received in this work, and thanks for your attention.
Thank you so much, Francesco. Thank you for sharing with us the interesting case of the polymer salt electrolyte. We have a good experience and competence built in Europe through Blue Solutions as is the coordinator of these projects, and it's a specific material gives us a little bit of leverage in terms of our scale, as we mentioned, but the performance indeed, as you mentioned, the synthesizers process and polymerization process needs better improvement. So thank you very much. Sorry, we have to move to the next presentation, but there is a question in Q&A. So Francesco, if you think you could write to our audience on the answers, please go ahead. So thank you. I move on to the next presentation.
Thank you for the opportunity. Bye.
Thank you so much. So our next presentation is from Project Advagen, and Rahmandika, I think, is with us, Rahmandika Firozja from Avesta Holding. So I'm gonna share the slides in a second. Oh, thank you so much. Good to have you.
Yeah.
Okay, I'm sharing the slide, Rahmandika, so please feel free to let me know to move to next slide. So please, the floor is yours.
Sure.
Thank you.
Thank you, Buzork, for this occasion. Actually, this is a good occasion to re-explain again about the Advagen project that maybe most of them, as the member of BEPA, already know Advagen since the RTR conference early of this year that we present in the Brussels. But that's progress. Maybe it's a bit months 18, months 24. But again, in this occasion, we'll try to explain about the progress until more or less month 36 or around July 2025. Yeah, this is the name of the long name of the project, which is somehow it's difficult to memorize, but yeah, the development of advanced next generation solid state batteries for electromobility application, which is we know Advagen. And yeah, my name is Rahmandika Firdausa Hariranda that will present today's presentation. Okay, we can go for next. This is the general overview of the Advagen project. Then for the next, yeah, the general overview, we can say 48 months project, same as Helena and Psionic, of course. And then with a total budget of this much, with 8 work packages and 14 partners from 9 countries. And yeah, for the detail, the next slide. The detail as Advagen Consortium, we have yeah, divided to several sections: material development, material processing, prototyping, characterization and testing, application, modeling, sustainability, and dissemination and communication and exploitation, of course. And yeah, why this in this project we have a material development, material processing, prototyping? Because here in Advagen, we try to, at that time in the proposal side in since 2022, we have a dream that okay, everything should come from Europe. So that's why in material development from NMC 811, we have Serpotec and IREC who developed that. And then with also CIC as the tester for the performance, and then TUBS as well to support for the compatibility with the LPSCL, and TUBS also producing the LPSCL on their own. That's why from this Advagen project we also have several patents application. That's one of them is the LPSCL from TUBS, and also module designed by Ikerlan. So yeah, and prototyping, we have Avesta here, CIC, and Ikerlan. So Avesta is working with prototyping beyond 1 ampere hour. CIC is working with the 1 ampere hour, and Ikerlan is working with the module design for the Advagen project. Yeah, and this is the overview. And then for the next slide, we can go with the uh, project itself, which is the cell itself. So we want to develop for the hybrid solid electrolyte, which is initially we try with the LPS and LLZO, but after several months we try, okay, LPS and LLZO have a problem with the compatibility. That's why we discuss with the PO, and then okay, we will adjust a bit with the LPSCL. So here we work with the sulfide oxide with the LPSCL and LLZO. And lithium metal anode, we develop a very thin lithium metal layer on copper foil by thermal evaporation, which is available in Vesta. And we try to develop as well with the protective layer, which is some kind of inorganic materials we try, and ceramic on top of the lithium metal. And nickel-rich oxide as cathode, this is what I mentioned, we also develop here in the project, which is we investigate with the NMC 811 interface optimization, evaluation, and further step for the upscaling. And yeah, here's the progress result. We can go for next slide. Okay, one more. Yeah. So yeah, I will try to deliver with this presentation one by one based on the objective. So that's why not really go imbalance with one objective deeper, one objective no. So we'll try to go with one by one objective. So in NMC 811 development in the Advagen project, we also try to approach with the different temperature and the synthesis atmosphere parameter. That's why here the different temperature we detect by, okay, with some kind of parameters like 700, 800, 850, and 900 degrees C, what's the effect in the NMC 811 making. So we detect by the XRD, and then we also check the carbonate appearance there by using FTIR. Then okay, then we can see the NMC 811 with different atmosphere synthesis atmosphere. It can show the different amount of the carbonate by the end of the product. And yeah, this is the result for the charge discharge when we try with the different temperature, which is the best one is 850 degrees C, because by that temperature we can maintain with the crystallinity of the NMC 811. And then with the atmosphere parameter, we also try with the several parameters with synthetic air, oxygen, and then with the air only. So that's why by these trials, by this approach, we can see, okay, which kind of atmosphere we can use to optimize the NMC 811 development. Here we can see that the synthetic air discharge capacity and also the discharge capacity of the oxygen, it shows different here. So that's why we have kind of a short conclusion there, which is with the oxygen we can have a good result in the capacity and also other performance. And in between, because we also need to maintain, because the oxygen also affect the lithium contained there, so that's why we need more excess lithium during the development. So that's why we add 10% extra lithium in oxygen atmosphere, so we can get the desired capacity that we want to go further. Even in the electrochemical performance, we can see with the oxygen synthetic air, there is a huge difference in the electrochemical performance. But here, once we involve the 10% extra of lithium and also oxygen, then we can see the balance between both. And here we see also the additional lithium as the post-treatment can get the capacity of NMC 811 kind of ideal capacity on beyond 200 milliampere hour per gram, and with quite sufficient cycle stability. So that's why in this project we also develop NMC 811 based on the consortium trials. So next, for the still in NMC 811 development, we go with the important notes here, which is to achieve better performance in NMC 811, at least we have 4 factors should be met. I think this approach is important for all of the industry or startup in Europe that want to try further with the NMC 811 or cathode active materials production. Then because in this approach, we need to maintain the high crystallinity, low cation mixing, and no carbonates with the correct stoichiometric. So this one should be balanced. And how to control that? Crystallinity, we have to control with the thermal treatment. Carbonates, we have control by the gas atmosphere, and stoichiometric, we have to control by the precursor. And then once we control all of this, then we have to characterize to detect the physical chemical properties with the at least with the XRD, FTIR, ICP, to maintain how the result of our product. And then again, if in the material characterization we don't have sufficient performance, then we come back to the how to control that. Okay, that's for the NMC 811. And the next is the hybrid oxide sulfide composite ceramic electrolytes and lithium metal anodes development. Here, this is what I mentioned in the beginning, that in the Advagen project, we developed the LPSCL, which is we can reach the LPSCL conductivity more than 1 millisiemens per centimeter for all batches, which has improved ionic conductivity for the hybrid solid-state battery system. And we also try to develop, this is what I mentioned, we also developed the protective layer on the lithium metal. Besides, we produce the lithium metal on copper by using thermal evaporation. We also try with the sputtering plasma for aluminum oxide coating optimization, and it's also successfully done there. And yeah, here, once we combine the LPSCL and also lithium metal anode, we have the stable performance at current density of more than 0.1 milliamp per centimeter square. And validation for all of them, like NMC 811 of Advagen, LPSCL, and also LZO hybrid, and then with the lithium metal, it's also validated in a coin cell. Even for the capacity is a little bit dropped than the original NMC 811 capacity, but it can categorize as the successful trials. And then for the next, with the demonstrating upscaled cell from 1 to 10 ampere hour pouch cell using an oxide sulfide hybrid electrolyte, nickel-rich cathode, and thin lithium metal in the pilot line. Yeah, unfortunately, we still not demonstrate here for the above 1 ampere hour, but here the trials for cathode layer manufacturing in the upscaling pre-pilot line stage towards 1 and 10 ampere hour cells with the catalyte using LPSCL, LLZO with the different ratios, we can reach quite stable performance here. Even the capacity is a bit lower. It's in the range of 60 to 80 milliampere hour per gram with the formulation of this much. So as you can see in the previous slide, maybe you can come back one more. Yeah, so here also we try to develop the ratio between LLZO and LPSCL. So this is the best performance that we can get, which is we use the LPSCL 80% and LLZO is 20%. So this is what we want to mention as the approach in this hybrid electrolyte. Then we can go next slide again. Again, next. Previous one, Buzor, maybe. Yeah. So after we see that okay, we have the stable performance here for the pre-pilot line, so that's why we try with the upscaling process, which is lab activity to the intermediate activity to the upscaling process somehow have their own challenge, because small batch of mixing and making slurry will be different with the bigger batch. And in the upscaling process of catalyte mixing, NMC811 produced in the Advagen project, mixed with LPSCL with the current solvent is still quite under optimization, because sometimes we have bubbling during the coating, and then yeah, this is the challenge that we can mention. The compatibility of NMC811 and LPSCL produced in the project with the solvent. So we have to make sure again, because in the small mixing we use some solvent which is okay, but when we move to the higher scale, which is we found like okay, with some amount of scale we have to change the solvent. So that's why here we still find the sedimentation problem during mixing. So we need to solve that one by one. And then by the end of I think end of March, April, we can get the good result in the catalyte making. And yeah, this is what I mentioned as well in the previous slides, that Ikerlan made the patent for the module design towards, even we still not reaching the 10 ampere hour yet, but at least the module design is already developed here. And for the next, as the next objective here is the next slide is the combined operando characterization technique with high time and spatial resolution for material selection. Here for Advagen battery cell, IREC settled the establishment of the collaboration with the ALBA synchrotron beamline, and responsible for the developing operando procedure, which is it's also from XRD, XAS, Raman, TERS, and then ellipsometry. Everything we try to see on how this NMC811 produced in this project performed well or not in the under the detection. And then there are several results which is still cannot show here all because of the confidentiality, but some of them already available in the published paper that I will show later. That were successfully conducted for inoperando measurement at synchrostructural and electrochemical characterization at, until the unit cell of the configuration. And then for the next, this is another objective as well for the developing multi-scale modeling for the battery components making and the battery electrochemical cell working mechanism. Here in the one side, we developed the mechanistic process model developed in the based on the process. We have the mixing, structuring, coating, drying, calendaring, and then it's mostly in the process structure relation and then process property relation. So we have to see between this process and structure how this process affect the mechanical, structural, and electrical properties of our analysis. And then we also see with this process on how electrochemical performance or electron and ion transport happen there, which is the electrochemical performance. And then we connect between structure and property in between the process structure property function, which is the target development here is the experiments connected with the mathematical function model. And also later we want to develop the prediction on, okay, if we have a process like this, how is the structure, how is the property. So this is the big goal. And all solid state lithium ion cell model here, which is with the approach of multi-scale model of the elementary electrochemical cell for the mapping implementation of the physicochemically consistent equivalent circuit model. Based on this model, we can try to consistently see that, okay, from the experiment, this is the blue line here from the EIS, we got that line, and then with the EIS simulation, we got the orange line, which is, yeah, maybe in the Warburg side, it's not that consistent, but from the RS and also RCT, we can see it's already near to the implementation. And then for the next objective, we can go with develop safer handling and recovery of various metal through sustainable recycling process, environmental impact and cost estimate. And yeah, this is just to mention, right before this presentation, I discussed with the recycling team of Avesta, which is how about the progress of this objective, which is, yeah, the first time we need to see the recycling target set in the battery regulation, which is recently um, declared as the applied for the battery regulation, which is there is a several percentage of metal and elements that need to recover. And then with the battery recycling pathway here, this is the conventional one. We have the discharging, dismantling, and sorting, and then directly go to thermomechanical pretreatment, pyrometallurgical treatment, and so on until the hydrometallurgical treatment. But here, because we also work with the lithium metal, of course, we have to think about, okay, how we can go with the direct recycling, and then how we can try to safely open the cell. So not only stop with the cell, then we shred, then we go with the black mass. No, we have to see on how, if we open the cell, is that safer, or we can try to eliminate some kind of if that cell directly going to shredding, then it somehow maybe the safety will be less. Then we can try to see prevent, okay, this electrode or this battery components can go directly to shredding, but this one we have to treat first. And here for the solvation test of lithium metal anode, and then we have delamination of cathode materials from aluminum foil. Why we did this? Because in lithium metal, of course, we have a lithium metal there, which is moisture sensitive, air sensitive, and anything. And then for the cathode materials, we also have LPSCl there, which is a bit tricky. And some innovative recycling routes following the previous proven result will be adapted to achieve an eco-friendly process with the consideration. And then we go with the next objective. In this Advagen project, we also want to develop a plan to market supported by strong collaboration through targeted communication and dissemination. But yeah, maybe with this kind of project, if we want to say, okay, plan to market is kind of a big goal. Yeah, of course. But at least with this big goal, we start with the small collaboration and synergy with the other project as well. So that's why here, through the networking activities and the roadmap to higher TRL task, Advagen is joining and actively participating in the Solid 4B cluster. And Advagen as the initial member as well for the Solid 4B cluster, together with the initiated by SpinMate project with Am4BATT, Hidden, Pulse Lion, Seatbelt, Solid, and Psionic. And then last year we got new members for Solve project, and then early this year we have Sprint project, because start from early of 2025 we decided in the Solid 4B cluster to, okay, maybe to extend the collaboration with other projects, with other entity in Europe. We can try to not close only for the lithium metal or solid state battery, but we can go with the beyond. So we go with the sodium, with the solid state solid state battery. So that's why Sprint joined. And then we go with the lithium metal production project. So here Stellar join, and then we go with the further lithium sulfur as well. And then, yeah, here we, in this 2025, we have 3 additional projects in the Solid 4B cluster. So this kind of clustering activity, which is sometimes we have a big event, which workshop hybrid event, like I think last several weeks, couple of weeks ago, we have a hybrid meeting with hosted by Pulse Lion and also Advagen in the hybrid webinar, and also in the several months forwards, we will have another workshop with hosted by Solid Project. Then with this, we can try to see not only from the communication and dissemination approach, but we can see also, okay, if I have this obstacle in this project, do you have the same thing? Or okay, we have the same thing, and how we tackle that, then we can exchange the information. And then for the next, I still have some conclusion then later. So in the long-term expected impact, we have the scientific, technology, and industrial here. Of course, based on all of the result, we put everything in the papers. We have around 5 papers here, which is some of them is still ongoing, and also the patents here from Ikerland, and also one ongoing from TUBS for the LPSCL making. And for the next, we also involved in the economic and societal and policy impact, which is we want to approach here. For the societal, of course, we stick with the open source and open science, which is we also put everything in the important deliverables and also important documents, which is open in the Zenodo, and we are part of the AU Open Research Repository there. So it's officially monitored by the CINEA. And then we can go with the summary and input. Yeah, here Advagen project has the, of course, all of the project. I think 3 of us here, I think from Helena, Psionic, Advagen has a challenging approach to match the R&D activities of our cell. Here in Advagen, we have a challenge with the hybrid sulfide oxide solid state electrolyte system, and then with those extra effort will be bravely tackled. We try with I think some of us will finish next year, so mid of 2026. Let's see what we can do by the rest of the time, and then later, if the result already, of course we have a major result there, but if we still not satisfied with that result, maybe we can go with another approach with see if as the example here we can go with the Advagen part 2, part 3, or beyond there. And yeah, I think that's all what I want to say. And then yeah, here please don't forget to join for everyone who is interested with the innovation of the battery development in Europe. Solid 4B cluster also become the exhibitor there. Yeah, see you there in 2-3 December in Kras. Thank you.
Thank you so much, Raimondika. Sorry, we went over time, but I didn't want to cut you off as your presentation was very passionate and very interesting. So thank you so much for that. Thank you for taking the time to joining us. And I re-invite our attendees to join us in the Battery Innovation Days and see for themselves the progress of all the projects in the Solid 4B cluster. I know you have an instrumental role in coordinating that cluster and making that coordination, as you mentioned, that we can expand. There are many common areas of activities that don't necessarily fit within the names of the cathodes or anodes, and it's the essence of the methodologies that could be shared. So thanks again. Thank you so much. We will hear much more from your projects, the projects in the cluster in the future webinar. So just very last point, please make sure to visit our website, subscribe to our newsletter if you would like to know more about the upcoming programs of BEPA, both open and also the ones exclusive to the members. So with that note, I wish you a very good day. Thank you all for joining us and attending, and see you in the next versions of BATT4EU Success Projects. Have a good day and thank you.
Yeah, thank you, Muzork, for hosting us.
Thank you.